This is Mars. Massive dust storms that can cover the entire planet for weeks. During these storms, rovers lose sunlight, solar panels stop working, and missions are put at risk. So here's a question for you. If you want to actually live and operate on Mars, how do we generate power when solar energy fails? What if the solution is already in the storm itself? That is exactly what my team, Tarun, Evan Madison, Hannah and Devin, and I, Leslie Nawa, research lead, worked at Georgia Tech through the VIP Mars program. And we asked a simple question while understanding those terms. Instead of fighting Martian dust storms, can we use them to generate energy? Now, here where triboelectric comes into place. So here's the idea. Triboelectric energy comes from contact and separation between materials. And on Mars, dust is constantly moving, colliding, and becoming electrostatically charged. So we thought, what if we design a system that captures that motion and turns it into electricity? So to test this, we built a full system to simulate Martian dust storms conditions. This setup let us control airflow, dust input, and materials interactions all in one system. We have a fan generating wind, a funnel controlling dust input, and inside the tunnel we line everything with PTFE and copper. These materials naturally generate charge when they interact, but the most important part is that we added internal flaps. These flaps move with the airflow, creating continuous contact and separation. That's where most of our energy comes from, and all of this connects to a circuit that lets us measure and store that energy. Now let's zoom in, guys, on how we control airflow and dust input. We designed this wind tunnel using Fusion 360 and SolidWorks to keep airflow control and consistent. The fan simulates high-speed Martian winds, while the funnel lets us introduce the dust in a controlled, repeatable way. And that consistency is key, because without it, we can't trust our data. And to make things more realistic, we did UV charging. We pre-charged the dust using UV light. We built a chamber lined with PTFE and exposed the dust to a 256 nanometer UVC light source. This knocks electrons off the particles, giving them a stronger charge before entering the system. Now, this is where things get a little bit more interesting. We introduced the flaps, flexible PTFE flaps inside the tunnel. As air flows through, the flaps start moving, constantly heating and separating from copper surfaces. So we have copper in the bottom, copper in the top, PTFE in the middle, and the flaps making those interactions. Every single contact creates charge, so more motion means more energy. Now, to actually use that energy, I designed and built the rectifying circuit. The flaps generate alternating currents, which normally cancels itself out. So that's when I use diodes to force currents to flow in one direction, from anode to cathode, preventing that cancellation. Then capacitors store the energy over time, and we use three 10 microfarad capacitors in parallel, giving us a total of 30 microfarads, as shown in the image, which lets us measure its stable voltage buildup, which we measure using a multimeter. Now we tested the system with and without this, changing the number of flaps and measuring voltage over time. And here, and you can see the flaps moving inside the tunnel, right? That motion is everything. Every time the flap hits and separates from the copper surfaces, boom, it generates a charge. So what you're watching here is energy being created in real time. And as you will see next, the motion directly translates into measurable voltage, which, this capacitor stores energy. And how do we measure that voltage? Using multimeter. Results, here we go. The results were exciting. Adding flaps significantly increased the voltage output, reaching out to about 3 volts, as you can see from the results. More flaps improved performance, though not perfectly linearly. Those charges were less consistent, but still show that charged particles contribute to energy generation. Overall, this confirmed that system design, especially flap interaction, is key to improving efficiency. That was our discovery. So now we understand from our references, reference, we are reference our fellow references, right? So instead of seeing Martian dust storms as limitations, we can start seeing them as an energy source. Because the future of space exploration isn't just about avoiding extreme environments, it's about learning how to use them. And maybe the same storms that once shut missions down could one day help power them. Thank you so much. This was Leslie Nava. I am an aerospace engineering student at Georgia Tech, and I'm happy to be presenting this, and thank you for listening.